Hello, my name is David Hurd, and this is my presentation of Lab 2, the motion of a falling object. Now first, let's go over some principles. The first one, namely the momentum principle, or Newton's second law, which says that a system's change in momentum is proportional to a net force on it. We're also going to be discussing the force of gravity, or the weight force, which is equal to mass times the constant g, which is about 9.8 meters per second. And this is a constant force. But we're also going to be looking at the drag force, which is caused by air resistance, which is a non-constant force, which is some proportionality constant times the velocity squared. We're also going to be using, once again, the position update and the velocity update formula, which is shown here in the code and here in the equation. Our initial conditions this time are an object, in this case 2 pieces of paper folded together into an almost bowl shape, with a mass of 0.009 kilograms, with an initial y position of 1.143 meters and an initial y velocity of 0, because it started at rest. The purpose of this lab is to observe a slowly falling object and create a computational model of its motion, and then to compare a computational and 2 predicted models, one accounting for air resistance and one that doesn't. And what we're going to see is that when you account for air resistance, it becomes much more accurate. Here is the object. Now, as you can see here, at rest, the paper will start with nothing but the weight force, and then as it starts moving, the drag force will increase, and then keep on increasing until it's going to reach what we call a terminal velocity, where the net force is 0, and it's going to stay at the same velocity. Now the tracker model, where we have the system as paper, and the surroundings are the earth, me, and the air, we have something interesting. You can notice at the very beginning there's a slight curve and a dip downward into what looks almost linear, which is strange for something that's accelerating. Here's the code. Now, as you can see, we calculated the weight with the same formula, and you'll notice that b, the proportionality constant, will be 0 when we don't want air resistance, and I made it 0.05 when there was. Now these are the 2 computational models. As you can see, with just gravity, you have a much more predictable parabola. But you can see how at about a second, it's already at -4. But when you look at with drag, you can see that same slight dip into a terminal velocity. And when you combine them, it becomes even more obvious because the model with gravity and drag matches it almost perfectly. Now, there are some stipulations and whatnot, because there's always going to be a little bit of error. My proportionality constant might be wrong, there might be some unaccounted forces, or I could have just tracked and done something wrong. Now, what does this all mean? Like the terminal velocity. The terminal velocity in this situation is when the net force is 0, which you can see when you put drag and air resistance into the equation. Of the 2 models, one very clearly has a point where it becomes almost linear, and that is when it is with drag. Now, what if you gave it an initial downward velocity? Now, the terminal velocity would still be the same, but get there at a different time, because the drag force is based off the velocity, and it'll equal the weight force, which doesn't change, when it is at that velocity. So we'll either slow down or speed up to get there, and it'll always end up at that terminal velocity at some point, given enough time. Thank you very much for watching this and listening, and have a nice day.